Welcome! In this session, we'll explore a fascinating problem titled Number of Steps to Reduce a Number in Binary Representation to 1. We'll break down the problem, analyze approaches, and uncover key insights. Let's dive in. In this problem, we are tasked with reducing a number, given in its binary representation as a string, down to 1. The process follows two simple rules: if the number is even, we divide it by 2, and if the number is odd, we add 1 to it. The process ends as soon as the number becomes 1, and our goal is to calculate the total number of steps required to achieve this. For the input, the binary string is guaranteed to represent a positive integer, meaning it won't have leading zeros. The size of the binary string can range from 1 to 500 characters, and the output will be a single integer that represents the total number of steps. Essentially, this problem asks us to simulate the given operations until we reach the number 1, counting every step along the way. Let's look at an example to clarify the process. Suppose the input binary string is 1101. This represents the decimal number 13. To reduce it to 1, we follow the given rules step by step. First, since 13 is odd, we add 1 to get 14. Then, 14 is even, so we divide it by 2 to get 7. Next, 7 is odd, so we add 1 to get 8. After that, 8 is even, so we divide it by 2 to get 4. Then, 4 is even, so we divide it by 2 to get 2. Finally, 2 is even, so we divide it by 2 to reach 1. Altogether, this process takes 6 steps. Therefore, the output for this input is 6. Now consider a simpler example. If the input binary string is 10, which represents the decimal number 2, the steps are straightforward. Since 2 is even, we divide it by 2 to get 1. This takes just one step, so the output is 1. For another example, if the input is 1, which already represents the number 1, no steps are needed. The number is already in the desired state, so the output is 0. The example where the input is 1 highlights an important edge case. When the binary string already represents 1, no operations are necessary, and the step count is 0. Let's also consider some additional constraints and edge cases. The binary string length can go up to 500 characters, so the solution must handle very large inputs efficiently. For instance, a string starting with 1 followed by 499 zeros represents a huge number, and the algorithm must be able to process it within reasonable time limits. Additionally, cases like 111, where all the digits are ones, need to follow the correct sequence of adding and dividing. These edge cases help ensure our solution is robust and handles a wide range of inputs effectively. To start, one straightforward approach to solving this problem is to simulate the given operations directly on the decimal value of the number. The intuition here is simple: since we need to reduce the number to 1, we can convert the binary string into its decimal equivalent and then repeatedly apply the operations. If the number is even, we divide it by 2, and if it's odd, we add 1. This process continues until the number becomes 1, and we count the steps as we go. While this approach is intuitive and easy to implement, its complexity includes the cost of converting the binary string to a decimal, which is O(n), plus the number of steps required to reduce the number to 1, denoted as k. This results in a total time complexity of O(n plus k, with a constant space complexity of O(1). However, as we'll see next, this approach has significant inefficiencies when applied to larger inputs. The primary drawback of the brute force approach lies in its inefficiency. By converting the binary string to its decimal equivalent, we lose the opportunity to leverage the structure of the binary representation. This results in unnecessary overhead, especially for very large inputs where this conversion and subsequent operations on the decimal number become computationally expensive. To address this, we can consider an optimized approach that works directly with the binary string. Here, the key idea is to bypass the conversion step entirely. In binary, dividing by 2 is equivalent to removing the least significant bit if the number is even, while adding 1 corresponds to propagating a carry in binary addition if the number is odd. By observing the binary structure, two main insights emerge. First, when the last bit is 0, it's an even step that simply reduces the binary string's length. Second, when the last bit is 1, the carry propagation can span multiple bits before the next operation. These insights allow us to process the binary string more efficiently, with operations tied directly to the binary representation. the optimized algorithm builds on the insights of directly manipulating the binary string. To implement this, we start by initializing a counter to keep track of the total number of steps. Then, we traverse the binary string starting from the least significant bit, which is the last character of the string, moving towards the most significant bit at the beginning. For each bit, we apply the rules. If the current bit is 0, it represents an even step, corresponding to a division by 2. If the bit is 1, we handle it as an odd step, which requires adding 1 and propagating the carry forward. This process continues until only the most significant bit, which is 1, remains, signaling the end of the reduction process. The advantage of this method is that each bit is processed exactly once, leading to a time complexity of O(n), where n is the length of the binary string. Space complexity remains constant at O(1). By directly operating on the binary structure, we eliminate the overhead of conversion and align the solution more closely with the nature of the problem. The optimized binary manipulation approach is ultimately the ideal strategy for this problem. The key insight was recognizing that the operations of division and addition directly align with simple manipulations of the binary string, such as removing bits or propagating carries. This allows us to avoid the inefficiencies of the brute force method, which required converting the binary string to decimal and performing arithmetic operations in that format. While the brute force approach is simpler to implement and may work for small inputs, it becomes computationally expensive for large binary strings. In contrast, the optimized approach is both more efficient and more elegant, with its time complexity of O(n) and minimal space usage. This makes it highly suitable for handling very large inputs. By leveraging the binary representation directly, we reduce unnecessary computational overhead and solve the problem in a way that is both efficient and tailored to the problem's constraints. In this problem, we are tasked with reducing a binary number, represented as a string, down to 1 using the minimum number of steps. There are 2 operations we can perform. If the number is even, we divide it by 2, and if it's odd, we add 1. The challenge is to determine how many operations are necessary to achieve this. To begin solving, we can take a brute force approach by first converting the binary string into its decimal equivalent. This conversion simplifies the arithmetic operations needed for the solution, such as division and addition. The conversion can be done in O(n) time, where n is the length of the binary string, using a loop to process each character. By iterating through the string, we compute the decimal value by multiplying the current result by 2 and adding the integer value of the binary digit. This gives us a straightforward way to work with the number in decimal form, which will be easier to manipulate for the subsequent steps. Once we have the decimal equivalent of the binary string, we initialize a counter to keep track of the number of operations performed. The goal is to repeatedly apply the specified operations until the number is reduced to 1. For each iteration, if the number is even, we divide it by 2 using integer division. If the number is odd, we add 1 to make it even, preparing it for division in the next step. After each operation, we increase the counter to reflect the step taken. This process continues until the number becomes 1, at which point we return the total count of operations. A key insight here is how the binary representation of numbers helps us understand these operations more intuitively. For example, dividing a number by 2 in binary is equivalent to performing a right shift, and adding 1 to an odd number flips its least significant bit and propagates any carry. This makes binary manipulation particularly efficient for solving this problem. Now, let's discuss why converting the binary string to a decimal number is a viable approach. While the input is given in binary format, working with its decimal equivalent allows us to use straightforward arithmetic operations like division and addition without directly manipulating the binary string. This simplifies the implementation. Furthermore, each division by 2 logarithmically decreases the size of the number, meaning the total number of steps required will be proportional to the number of bits in the binary representation. In terms of data structures, we rely on simple integer variables, one to store the decimal representation of the number and another to count the operations performed. This minimal use of memory ensures the algorithm remains space efficient. By focusing on these operations and their efficiency, we can ensure the solution performs well even for large inputs. Analyzing the complexity of this approach, the time required to convert the binary string to a decimal number is O(n), where n is the length of the string. For the subsequent operations, each division or addition reduces the number logarithmically, leading to O log m steps, where m is the decimal value of the input. Combining these, the overall time complexity is O n plus log m. Space-wise, the algorithm uses only a constant amount of additional space, O1, since we only maintain a few integer variables. To ensure correctness, we should also account for edge cases. For instance, if the input binary string is 1, the number is already 1, so no operations are needed, and the algorithm should return 0. For very large binary strings, the algorithm must handle inputs of up to 10 to the power of 5 bits efficiently, which is achievable with integer arithmetic. Additionally, invalid inputs like binary strings consisting only of zeros should be sanitized before processing to avoid errors. Let's walk through an example to understand the process. Consider the binary string 1101, which represents the decimal number 13. First, we convert it to its decimal form, which is 13. Now, we apply the operations step by step. In the first step, 13 is odd, so we add 1 to get 14. In the second step, 14 is even, so we divide by 2 to obtain 7. Next, 7 is odd, so we add 1 again to get 8. Then, 8 is even, so we divide by 2 to get 4. Dividing 4 by 2 results in 2, and finally, dividing 2 by 2 gives us 1. This sequence takes a total of 6 operations. This example demonstrates how the algorithm systematically reduces the number using the specified operations. To optimize further, we can explore avoiding the initial binary to decimal conversion and directly manipulating the binary string instead, thereby eliminating the O(n) conversion cost. One way to optimize the solution is by leveraging bitwise operations directly on the binary representation. For example, instead of performing arithmetic division, we can use a right shift operation, which is computationally faster. Similarly, checking whether a number is even or odd can be done using a bitwise AND operation with 1, as the least significant bit determines parity. These bitwise operations are not only efficient but also align naturally with the binary format of the input. By avoiding unnecessary conversions and utilizing these low-level operations, the implementation becomes faster and more tailored to the problem at hand, ensuring it scales well even for very large binary strings. The given problem requires reducing a binary number, represented as a string, to 1 by applying specific operations. The operations include dividing by 2 if the number is even or incrementing the number by 1 if odd. The goal is to compute the minimum number of steps required. Here is the breakdown of the solution. 1. Initialization. The steps variable is initialized to 0 to keep track of the number of operations. The binary string s is converted to a list of characters for easier manipulation since strings are immutable in Python. 2. Main loop. The loop runs until the binary number reduces to 1, which corresponds to the termination condition len, s1. 3. Even case. If the last digit of the binary number is 0, the number is even. In binary, dividing by 2 is equivalent to removing the last digit. This is implemented with s.pop. For odd case, if the last digit is 1, the number is odd, so we add 1. Binary addition involves propagating a carry if the current digit is 1. Starting from the last digit, we replace consecutive ones with zeros and move leftward until a 0 is found. This 0 is flipped to 1. If all digits are 1, e.g., adding 1 to 111, we prepend a 1 to the list using s.insert 0, 1. 5. Increment steps. After each operation, either divide by 2 or add 1, we increment the steps counter. 6. Return result. Once the binary number reduces to 1, the loop exits, and the total count of steps is returned. This approach efficiently handles the problem by simulating the operations directly on the binary representation, avoiding the need for conversion to decimal. The algorithm processes each bit at most once, making it highly efficient for binary strings of any length. Here, we start by defining the number steps method, which takes a binary string s as input. We initialize a variable steps to 0, which will count the number of operations required to reduce the binary number to 1. We also use a string builder to represent the binary number because it allows us to efficiently modify the string during the process. The while loop continues as long as the binary number is more than 1 digit, meaning it hasn't been reduced to 1 yet. Inside the loop, we check the last digit of the binary number. If the last digit is 0, we execute a division by 2 by simply removing the last digit using the deleteCharet method. On the other hand, if the last digit is 1, we need to increment the binary number by 1. This involves traversing backwards through the string and flipping all trailing ones to zeros until we encounter a 0, which we then flip to 1. If all bits are 1, we prepend a 1 to the string to handle the carry. Each operation increments the steps counter, ensuring we keep track of how many steps we've performed so far. Finally, after the loop ends, the binary number has been reduced to 1, and we return the total number of steps we calculated. This completes the implementation of the number steps method, which follows the given problem requirements and handles both the division and addition operations efficiently. The use of a string builder here makes the manipulation of the binary number straightforward, enabling us to focus on the core logic of the problem while maintaining good performance. With this, the solution is complete. Let's start with the binary string s equals 1101. Initially, the binary string is represented as a list of characters, 1, 1, 0, 1, and we set our step counter to 0. Now, in the first step, the last digit is 1, which is odd. When the binary number is odd, we add 1 to it. To perform this binary addition, we start from the last digit, change 1 to 0, and the carry propagates. Moving to the next digit, we change 0 to 1. After the addition, the binary number becomes 1, 1, 1, 0. We increment the step counter, so steps is now 1. In the second step, the last digit is now 0, which is even. For even numbers, we remove the last digit, which is equivalent to dividing the binary number by 2. The new binary number is 1, 1, 1, and we increment the step counter again to steps equals 2. In the third step, the binary number ends with 1, which is odd. We add 1 to the binary number again. Starting from the last digit, we change 1 to 0, and the carry propagates. The next digit is also 1, so we change it to 0, and the carry propagates further. Finally, the next digit is 1 as well, so we change it to 0 and prepend 1 to the binary number. The result of this addition is 1, 0, 0, 0. We increment the step counter, making steps equals 3. In the fourth step, the last digit is now 0, which is even. We remove the last digit, and the binary number becomes 1, 0, 0. Incrementing the step count gives us steps equals 4. In the fifth step, the last digit is still 0, so we remove it again. The binary number is now 1, 0, and we increment the steps to steps equals 5. In the sixth step, the last digit is still 0, so we remove it once more. At this point, the binary number becomes 1, which is simply 1. Since we've reduced the number to 1, we stop here. The total number of steps taken is 6. Now, let's look at another example with the binary string s equals 10. Initially, s is represented as 1, 0, and the step counter is 0. In the first step, the last digit is 0, which is even, so we remove it. The binary number is now 1, and we increment the step counter to steps equals 1. At this point, the binary number is already 1, so we stop. The total number of steps for this example is 1. For the example where s equals 10, the final output is 1. Now let's move on to the binary string s equals 111. Initially, the binary string is represented as 1, 1, 1, and the step counter is set to 0. In the first step, the last digit is 1, which is odd. We add 1 to the binary number. Starting from the last digit, we change 1 to 0, and the carry propagates. The next digit is also 1, so we change it to 0, and the carry propagates again. The next digit is 1 as well, so we change it to 0 and prepend 1 to the binary number. The result of this addition is 1, 0, 0, 0. We increment the step counter, making steps equals 1. In the second step for s equals 111, the last digit is 0, which is even. We remove the last digit, and the binary number becomes 1, 0, 0. Incrementing the steps gives us steps equals 2. In the third step, the last digit is again 0, so we remove it. The binary number is now 1, 0, and the step counter becomes steps equals 3. In the fourth step, the last digit is still 0. Removing this digit leaves the binary number as 1, which is 1. At this point, we stop since the number has been reduced to 1. The total number of steps for this example is 4. To analyze the time complexity of the algorithm, we start by breaking down its operations. When the binary string represents an even number, the last digit is a 0. The algorithm handles this by performing a simple pop operation to remove the last digit, which takes constant time, or O1. However, when the number is odd, the algorithm adds 1 to the binary representation. This addition introduces a carry that may need to propagate through the entire string. For example, adding 1 to a binary number like 111 results in a carry propagating through all bits, turning it into 1000. In the worst case, this propagation takes n time, where n is the length of the binary string. These two cases form the building blocks of the algorithm's time complexity analysis. Now, let's consider the overall time complexity. Each iteration of the while loop involves either an O1 division by 2 operation or an O(n) binary addition operation in the worst case. The number of iterations corresponds to the number of steps required to reduce the binary number to 1. For a binary string of length n, the number of steps is proportional to the number of bits, which is O(n). Additionally, since each bit contributes to a carry propagation at most once during the entire process, the overall time complexity remains O(n). Moving on to space complexity, the algorithm converts the input binary string into a list of characters. This requires O(n) space. Beyond this, only a few auxiliary variables are used, meaning the additional space required is O(1). Thus, the total space complexity is dominated by the storage of the binary string, which is O(n). When looking at the overall space complexity, we conclude that the algorithm requires O(n) space to store the list representation of the binary string. To better understand the efficiency of this approach, let's compare it to a brute force method. A naive solution might involve repeatedly converting the binary string into an integer, performing arithmetic operations, and then converting the result back into binary. However, these repeated conversions are expensive, each taking O(n) time. Over multiple iterations, this leads to a total time complexity of O(n) squared. In contrast, the current algorithm avoids these conversions by directly manipulating the binary string. This optimization allows it to achieve an overall time complexity of O(n), making it much more efficient. Finally, let's analyze the algorithm across best, average, and worst case scenarios. In the best case, the binary number is a power of 2, meaning all operations are simple divisions by 2. Since each division takes constant time, the overall time complexity remains O(n). In the worst case, the binary number contains many ones, leading to frequent carry propagations during addition. Even in this scenario, each bit contributes to the propagation only once, so the time complexity is still O(n). For the average case, a random binary string of length n will have a mix of zeros and ones, resulting in a combination of divisions and additions. This balanced distribution keeps the time complexity O(n) on average. Mathematically, since each bit is processed at most once for either division or carry propagation, the total number of operations is directly proportional to n. This confirms the time complexity is O(n). When solving this problem, there are several common mistakes to watch out for. First, handling binary strings with leading zeros is critical. Binary numbers like 00101 are valid, but if you skip over the leading zeros when converting to integers, your solution might fail. Next, inefficient decimal conversions can slow down your approach. If you're repeatedly converting between binary and decimal forms during simulations, you're adding unnecessary overhead. Instead, directly manipulate the binary string to simulate the operations and save time. Another frequent issue is overlooking edge cases. For instance, if the binary string is already 1, the solution should immediately return 0 steps, but failing to account for this can lead to errors. Misinterpreting the sequence of operations is another pitfall. For example, subtracting before dividing, when the rules specify the opposite, can result in incorrect logic. Finally, be cautious about overflow concerns. Directly converting very large binary strings into decimal integers can cause overflow problems in some programming languages. To avoid this, work with the binary representation as much as possible or use modular arithmetic where needed. In interviews, solving this problem often goes beyond just finding a correct solution. Recognizing the underlying patterns in binary operations, such as how division by 2 or subtraction by 1 can be mapped to bitwise manipulations, is crucial. This insight allows you to simplify your implementation and optimize for performance. While brute force methods can solve the problem, interviewers typically look for more efficient solutions that work directly with binary properties and avoid unnecessary decimal conversions. Additionally, communication is key during these interviews. Clearly articulate your thought process, especially how you address edge cases and optimize your approach. Interviewers appreciate clarity and logical reasoning as much as the correctness of your code. Lastly, be prepared to discuss time complexity. Explain the trade-offs between a brute force approach, which might have a time complexity of O(n) squared, and an optimized solution with O(n) complexity, where n is the length of the binary string. This problem also connects to several related problems that can help you build a deeper understanding of binary operations. For example, LeetCode 67, add binary, involves direct manipulation of binary strings. LeetCode 191, number of 1 bits, focuses on counting bits in a binary representation, while LeetCode 231, power of 2, explores properties of binary numbers. Lastly, LeetCode 405, convert a number to hexadecimal, deals with conversions between numeral systems. Now, there are also alternative approaches to this problem that you might consider. A greedy approach involves analyzing the binary string from right to left. Trailing zeros indicate division steps, while ones require a subtraction or an addition. This method minimizes the number of operations you simulate. Alternatively, bitwise manipulation allows you to directly work with the binary representation of the number, avoiding the overhead of conversions. Lastly, a recursive solution can simulate the operations step by step. While less efficient than iterative methods, recursion is often easier to debug and can showcase your understanding of the problem's mechanics. Finally, let's discuss the trade-offs between different approaches. A brute force solution is straightforward to implement and can help you quickly verify your understanding of the problem. However, it can be slow for larger inputs due to its repeated conversions and operations, which increase runtime complexity. On the other hand, approaches like bitwise manipulation or greedy strategies are much more efficient. These methods require a deeper understanding of binary arithmetic, but they significantly reduce computational overhead. The challenge with these optimized solutions lies in their careful implementation, as even small mistakes can lead to bugs. Choosing the right approach depends on the context, whether you're practicing for interviews, optimizing for performance, or simply learning the fundamentals of binary operations. Thanks for joining. We reviewed the problem, explored approaches, and highlighted key takeaways. Don't forget to practice similar problems and continue sharpening your coding skills. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!